Ever tried making sense of messy, overlapping data? That's where Partial Least Squares Regression, PLSR, steps in. It's like giving your data a translator, turning chaos into clear, predictive insights. Think of it as the love child of principal component analysis and multiple regression, designed to handle collinearity while keeping the most important information intact. We'll start with what PLSR actually is, why it's better than principal component regression in certain cases, and how it works behind the scenes with latent variables and projections. Then we'll break down its step-by-step application from data prep to model validation so you can use it confidently. But it's not all sunshine and perfect predictions. PLSR has its challenges: computational demands, interpretation complexity, and overfitting risks. We'll cover those and compare it to multiple linear regression to help you decide when it's the right tool for the job. And to prove it's more than just fancy math, we'll look at real-world applications in chemometrics, genomics, and social sciences. Finally, we'll explore what's next for PLSR, including its role in machine learning and big data. By the end, you won't just know PLSR, you'll know when, why, and how to use it. Let's dive in. So, you've got a data set that looks like a tangled mess of spaghetti, variables all over the place, correlations twisting in ways that make no sense, and somehow you're expected to extract meaningful insights from it. That's where partial least squares regression, or PLSR, comes in. Think of it as a statistical superhero stepping in to save you from data chaos. It's like principal component analysis and multiple regression had a really smart child who actually knows how to handle multicollinearity and high dimensional data. PLSR is all about finding patterns in your data without letting unnecessary noise distract you. Unlike traditional regression, which gets overwhelmed when predictors start whispering secrets to each other, aka correlation, PLSR turns that complexity into a strength. It works by projecting your data into a new space where the most important information shines through, cutting out the fluff while keeping what actually matters. It's kind of like trying to listen to your friend at a loud party. PLSR finds the signal and tunes out the noise. But here's the kicker. PLSR isn't just some fancy theoretical tool collecting dust in textbooks. It's used in everything from predicting chemical reactions to analyzing social behavior and even understanding gene expression in genomics. This method is like a Swiss Army knife for data analysis, versatile, powerful, and sometimes the only tool that gets the job done. So if you've ever looked at your data and thought there's got to be a better way to make sense of this mess, congratulations, you're in the right place. We're about to break down PLSR, how it works, why it's better than some other methods, and when you should and shouldn't use it. By the end of this, you won't just understand PLSR, you'll know how to make it work for you. Let's get started. Ever had two things that seem almost the same but turn out to be totally different, like margarine and butter or decaf and real coffee? That's the situation with partial least squares regression, PLSR, and principal component regression, PCR. People mix them up all the time, but trust me, they work in very different ways. And if you use the wrong one, your data might just laugh at you behind your back. So here's the deal. Both PLSR and PCR aim to reduce dimensionality, meaning they take a chaotic jungle of variables and turn it into something more manageable. But the way they do it, that's where things get interesting. PCR starts by doing a principal component analysis, PCA, on your predictors and then runs regression on those transformed variables. Sounds fine, right? Well, here's the catch. PCR doesn't care one bit about the response variable while creating these components. It's like picking players for a basketball team based only on height without checking if they can actually play. PLSR, on the other hand, is way smarter. Instead of blindly reducing dimensionality, it finds new components that maximize the covariance between predictors and the response variable. Translation: PLSR builds its components in a way that actually improves prediction. Imagine hiring a chef not just because they own knives, but because they can actually cook. That's the difference between these two methods. So, when should you use PLSR over PCR? If your predictors are highly correlated and you actually care about making good predictions, which, let's be honest, you do, PLSR is the way to go. If you just want to reduce dimensionality without focusing on prediction quality, PCR might be enough, but if you're here, I'm guessing you're aiming for the best results possible. In that case, PLSR is your new best friend. Ever been in a group project where one person does all the work and the rest just sit there pretending to contribute? That's kind of how regression works when your predictors are highly correlated. Some variables carry all the real information, while others are just along for the ride, adding noise and making your life miserable. Enter Partial Least Squares Regression, PLSR, and Principal Component Regression, PCR, two methods that step in to fix the mess. But just like group project members, not all methods are equally helpful. Both PLSR and PCR have the same basic goal: simplify complex, messy data by reducing dimensionality. Think of it as trying to condense a 500-page novel into a one-page summary. But here's the thing. PCR and PLSR go about it in completely different ways. PCR starts by running Principal Component Analysis, PCA, on your predictor variables, finding the directions with the most variation, and then using those new components for regression. Sounds reasonable, right? But there's a flaw. PCR doesn't care about the response variable at all. It just finds the biggest trends in the predictor variables without considering whether they actually help predict your outcome. It's like hiring someone based on their impressive resume, only to find out they can't actually do the job. PLSR, on the other hand, is the method that actually thinks ahead. Instead of blindly picking the components with the most variation, it finds the ones that are most useful for predicting the response variable. It's like hiring someone who not only has a great resume, but also has the skills to get the job done. Instead of just summarizing the predictor data, PLSR builds components that maximize the relationship between predictors and the response, making it much more powerful for real-world applications. So when do you pick PLSR over PCR? Simple. When your predictors are highly correlated and you actually care about getting accurate predictions. PCR is useful for reducing complexity when prediction isn't your main goal, but if you need a model that actually performs, PLSR is the way to go. It's the difference between throwing darts blindfolded and actually aiming at the target. So unless you enjoy rolling the dice on your regression models, PLSR is the method you want in your toolkit. You wouldn't bake a cake by tossing random ingredients into a bowl and hoping for the best, right? Same goes for Partial Least Squares Regression, PLSR. If you want results that actually make sense, you need a structured approach, because even the most powerful model is useless if your data is a disaster. So, let's break it down. The essential steps to conducting PLSR properly. First up, data preparation, or as I like to call it, clean up your mess before you embarrass yourself. This means collecting all relevant variables, handling missing values, normalizing data if needed, and removing redundant junk that could mislead your model. Think of it like prepping ingredients before cooking. If you start with bad inputs, don't expect a masterpiece. Next, we move on to model fitting, where PLSR does its thing. The key here is selecting the right number of latent components. Too few, and you miss crucial information. Too many, and your model starts memorizing random noise instead of actual patterns. Hello, overfitting. It's like seasoning food. Get it right and everything comes together. Overdo it and you regret every bite. Now we get to model validation, the step that saves you from false confidence. Here, we check if the PLSR model performs well, not just on the training data, but also on new unseen data. Cross-validation is the gold standard for this, where we split the data set into training and testing parts. Skip this, and you're basically building a house without checking if the foundation is solid. Looks fine until everything collapses. Finally, it's time for result interpretation. figuring out if all this effort actually paid off. You'll analyze which predictors matter, how well the model explains variance, and whether its predictions make sense. PLSR makes this slightly tricky since we are dealing with latent variables instead of directly measurable ones. But once you understand how to read the output, you'll see why this method is a game changer. So that's it. Clean data, smart model fitting, rigorous validation, and careful interpretation. Miss a step, and you're playing statistical roulette. Get it right, and PLSR becomes your secret weapon for uncovering hidden relationships in data that other methods completely miss. Data is everywhere, but making sense of it, that's where the real challenge begins. Thankfully, Partial Least Squares Regression, PLSR, isn't just some fancy math trick. It's actually making a huge impact across multiple industries, from predicting chemical reactions to understanding social behavior and even analyzing DNA. This method is quietly shaping the world around us. Let's take a look at how PLSR is used in some of the most unexpected and fascinating ways. First up, chemometrics, the science of measuring and analyzing chemical data. PLSR is used here to predict how different compounds interact, optimize chemical processes, and ensure quality control in industries like pharmaceuticals, food production, and manufacturing. Imagine a lab full of scientists trying to fine-tune the perfect formula for a new drug. PLSR helps them cut through the complexity and find the optimal mix of ingredients. Then we have genomics, where researchers deal with massive data sets full of genetic information. PLSR is crucial for identifying biomarkers, predicting disease risks, and understanding how genes influence health. Think of it as a detective for DNA, connecting the dots between genetic variations and real-world health outcomes. Without it, sifting through genetic data would be like trying to read a novel with all the pages out of order. In social sciences, PLSR helps researchers analyze complex survey data and understand relationships between social variables. Whether it's studying economic trends, public opinion, or consumer behavior, this method allows researchers to extract meaningful patterns from noisy, overlapping data. Ever wonder how marketers predict what you're going to buy before you even think about it? Yep, they might be using something like PLSR. The pharmaceutical industry is another big fan of PLSR. Drug development is a high-stakes game where small mistakes cost millions. PLSR helps scientists model how different chemical properties affect drug performance, speeding up the development process and reducing trial and error experimentation. It's basically like having a cheat code for pharmaceutical research. And let's not forget environmental science. From tracking pollution levels to studying climate patterns, PLSR is used to model complex environmental systems and predict how different factors interact. It helps scientists understand the impact of pollutants on ecosystems, making it a crucial tool in sustainability research. Bottom line, PLSR isn't just an abstract mathematical concept sitting in a dusty textbook. It's actively being used to solve real-world problems in medicine, science, business, and beyond. Whether you're analyzing chemicals, genes, opinions, or ecosystems, this method has the power to uncover hidden insights and make better predictions. Pretty impressive for something most people have never heard of, right? Some statistical methods feel like they're just making your life harder. PLSR, on the other hand, actually makes things easier, like a good assistant that knows exactly what you need before you even ask. So, what makes Partial Least Squares Regression, PLSR, so great? Let's talk about the advantages that make it stand out from other regression techniques. First off, it handles multicollinearity like a pro. Regular regression models panic when predictor variables are highly correlated, throwing errors and making your coefficients unreliable. PLSR doesn't just deal with multicollinearity, it embraces it, using projections to reduce complexity while still keeping the most important information. It's like turning a cluttered desk into an organized workspace without throwing anything important away. Another major win. PLSR works even when you have a small sample size. Most regression techniques demand huge datasets to produce reliable results, but PLSR can make accurate predictions even with limited data. This makes it especially useful in fields like medicine and genomics, where collecting large samples is often expensive, time-consuming, or just not possible. Think of it as getting solid insights from just a few puzzle pieces instead of needing the whole picture. Then there's dimensionality reduction, which is a fancy way of saying PLSR helps you focus on what really matters. When you have dozens or even hundreds of predictive variables, regular regression models get overwhelmed. PLSR condenses them into a smaller set of meaningful components without losing crucial information. It's like compressing a high-resolution image without losing quality. Less bulk, same clarity. It also shines when it comes to predictive accuracy, since PLSR builds its components by maximizing the relationship between predictors and the response variable. It's naturally better at making accurate predictions than methods that just summarize data blindly. Looking at you, Principal Component Regression. If you care about getting the best possible predictions, PLSR is your go-to. And lastly, it improves model interpretability, which sounds ironic since PLSR is often criticized for being tricky to interpret. But here's the thing, it actually makes your results more meaningful by reducing noise and focusing on the variables that matter most. Instead of drowning in a sea of insignificant predictors, you get a cleaner, more interpretable model. It's like having subtitles for a foreign movie. Suddenly, everything makes sense. So, to sum it up, PLSR handles correlated predictors effortlessly, works even with small datasets, reduces complexity, boosts prediction accuracy, and makes your model easier to work with. Not bad for a method that most people have never heard of, right? Not everything in life is perfect, not even PLSR. Sure, it's powerful, flexible, and great at handling messy, high-dimensional data, but it comes with a few quirks that can trip you up if you're not careful. Let's talk about the limitations of partial least squares regression, because knowing where it struggles is just as important as knowing where it shines. First up, interpretation complexity. PLSR loves working with latent variables, but that means the original predictors get transformed into abstract components. Unlike traditional regression, where you can directly interpret coefficients, PLSR makes you do a bit of detective work to understand what's actually influencing your results. It's like trying to understand a conversation when half the words have been replaced with emojis. You get the general idea, but it's not as clear as you'd like. Then there's overfitting risk. PLSR is great at finding patterns, but give it too many components and it might start seeing patterns that don't actually exist. It's like reading too much into a text message. Sometimes OK just means OK, not a secret code. If you're not careful, your model might perform brilliantly on your training data, but fail miserably when faced with new information. Cross-validation is your best friend here. Another challenge is computational demand. PLSR isn't exactly lightweight, especially when dealing with massive datasets. Because it involves matrix calculations and iterative optimization, it can be resource intensive, which might slow you down if you're working with really large or real-time data. If traditional regression is like riding a bike, PLSR can feel more like flying a spaceship. Powerful, but you better have the right tools to handle it. And then there's data requirements. PLSR may handle small sample sizes better than some methods, but it still needs enough high-quality data to work well. If your data set is too small or full of noise, PLSR might struggle to extract meaningful relationships, leaving you with results that are about as useful as a broken GPS. Finally, model stability can be an issue. Because PLSR relies on projections, small changes in the data can sometimes cause noticeable shifts in the model output. This means your results might not be as stable as you'd expect, making it tricky when working with sensitive datasets where consistency is key. So, while PLSR is an incredibly useful tool, it's not a one-size-fits-all solution. If you need an easy-to-interpret model or if computational efficiency is a top priority, you might want to look elsewhere. But if you're working with complex, high-dimensional data and need a method that balances dimensionality reduction with predictive power, PLSR is still one of the best tools in the game. Just make sure you know its limits before you put all your trust in it. Regression models are like tools in a toolbox. You don't use a hammer for every job, and you definitely don't treat a screwdriver like a wrench. The same goes for partial least squares regression, PLSR, and multiple linear regression, MLR. Both are powerful, but they solve problems in very different ways. If you've ever wondered when to use PLSR instead of standard MLR, this is where things get interesting. Let's start with model complexity. MLR assumes a nice, clean, straight-line relationship between predictors and the response variable. But in the real world, data is messy. Predictors are often correlated, relationships aren't always linear, and traditional regression starts falling apart when things get too complicated. PLSR, on the other hand, is built to handle complexity. It reduces the dimensionality of the data and finds the most important patterns, making it far more reliable when dealing with high-dimensional datasets. Then there's multicollinearity, a fancy word for when predictors are so closely related that MLR throws a tantrum. When predictors are highly correlated, MLR struggles because it assumes each variable contributes independently to the outcome. This leads to unstable coefficients and misleading results. PLSR sidesteps this issue by creating new latent variables that capture the most meaningful information while ignoring redundant noise. It's like having a translator that helps you understand a room full of people all talking at once. Another key difference: number of predictors. MLR does fine when you have a handful of independent variables, but throw in dozens or even hundreds, and it starts to crumble under the weight of too much information. PLSR thrives in these situations. Whether you're working with gene expression data, spectral analysis, or complex social science variables, PLSR can reduce hundreds of predictors into a much smaller set of meaningful components. But here's the catch: interpretability. MLR is straightforward. Each predictor gets a coefficient, and you can see exactly how much it contributes to the outcome. PLSR, on the other hand, transforms the predictors into latent variables, making interpretation a bit trickier. You don't get a simple increase x by 1 and y increases by 3 type of relationship. Instead, you need to analyze which latent variables matter most and what they represent. If transparency is a priority, MLR might be the better choice. Finally, prediction versus explanation. If your goal is to explain relationships clearly and directly, MLR is your guy. If you care more about accurate predictions and handling complex data structures, PLSR is the smarter pick. It's the difference between a professor giving you a detailed explanation and an AI that just spits out the right answer without telling you why. So, which one should you use? If you have a small, clean data set with independent predictors and you need straightforward explanations, go with MLR. If you're dealing with multicollinearity, a ton of predictors, or high-dimensional data where prediction is the goal, PLSR is the way to go. Choosing the right method is half the battle. Pick the wrong one, and you might end up explaining noise instead of finding real insights. Science is full of complex data, and chemometrics is no exception. If you've ever wondered how scientists fine-tune chemical formulas, optimize production processes, or predict how a new material will behave, partial least squares regression, PLSR, is often behind the scenes making it all possible. In this case study, we'll explore how PLSR is used in chemometrics to make sense of highly correlated chemical data. Let's start with the challenge. Chemical datasets are notorious for having too many variables and not enough samples. Imagine trying to determine the perfect coffee blend by testing 100 different factors: roast level, bean origin, grind size, water temperature, but you only have 20 cups to taste. That's the situation chemists face when trying to model chemical properties. Standard regression methods would struggle, but PLSR, it thrives under these conditions. Now, let's apply it to spectroscopy, a technique used to analyze the composition of substances based on how they absorb or emit light. Spectral data involves hundreds or thousands of wavelengths, all of which are correlated. PLSR helps by reducing this massive dataset into a few key latent variables that still capture the essential chemical information. Instead of drowning in data, researchers get a clear picture of which wavelengths actually matter. Another big win for PLSR is quality control in manufacturing. Let's say a company wants to predict the concentration of an active ingredient in a pharmaceutical drug based on spectral readings. Traditional methods would struggle with noisy, overlapping signals, but PLSR cuts through the clutter, creating a reliable model that predicts ingredient levels with high accuracy. This not only speeds up production, but also ensures consistency and safety in products like medicine, food, and industrial chemicals. And speaking of efficiency, PLSR is also a go-to for process optimization. Imagine a chemical plant that wants to maximize yield while minimizing waste. Instead of running endless experiments, which can be expensive and time-consuming, they can use PLSR to model how different factors influence the final product. The result? More efficient production, lower costs, and fewer surprises. In short, PLSR is a powerhouse for chemometric analysis. It takes messy, complex, high-dimensional chemical data and turns it into meaningful, actionable insights. Whether it's predicting molecular properties, analyzing spectroscopic data, or ensuring product consistency, this method has become an essential tool for scientists and engineers alike. Without it, we'd probably still be relying on trial and error. So next time you take a perfectly formulated medicine or sip a consistently delicious soda, remember that PLSR might have had something to do with it. Genomics is like trying to read a million books at once. Each gene is a chapter, each expression level a sentence, and somehow scientists have to figure out which parts actually matter. With massive datasets and complex relationships between genes, partial least squares regression, PLSR, has become a crucial tool in genomic research, helping scientists uncover patterns that would otherwise be buried in noise. The challenge in genomics isn't just the sheer volume of data, but the fact that most of it is highly correlated. Gene expression studies, for example, involve thousands of genes interacting in ways that aren't always obvious. Traditional regression methods would crumble under the weight of this complexity, but PLSR, it thrives. By reducing thousands of predictors, gene expression levels, into a small number of latent variables, PLSR helps researchers focus on the most relevant patterns without losing critical information. One of its biggest applications is in biomarker discovery, identifying which genes are linked to specific diseases. Let's say scientists are studying cancer patients and want to find which genes are most predictive of tumor growth. Instead of analyzing each gene separately, which would take forever and lead to misleading correlations, PLSR finds combinations of genes that best explain disease progression. It's like turning a chaotic crime scene into a clear suspect profile. Another major use? Personalized medicine. Different patients respond to treatments in different ways, and genomic data holds the key to predicting which treatments will work best for whom. PLSR helps by linking gene expression profiles to drug response, allowing doctors to tailor treatments to individual patients. This means fewer ineffective treatments and a better shot at getting it right the first time. Kind of like Netflix recommendations, but for medicine instead of movies. PLSR also plays a huge role in predicting disease risk. By analyzing genomic data from thousands of individuals, researchers can build models that estimate the likelihood of developing conditions like diabetes, heart disease, or Alzheimer's. These predictions don't just help with early detection, they also guide lifestyle and medical interventions long before symptoms appear. And if that wasn't enough, PLSR is also making strides in gene-environment interactions, studying how genes and external factors like diet, pollution, or stress work together to influence health outcomes. These interactions are notoriously hard to capture using traditional statistical methods, but PLSR's ability to handle high-dimensional, noisy data makes it one of the best tools for the job. So, what's the takeaway? PLSR is revolutionizing genomics by making sense of overwhelming amounts of data, identifying critical biomarkers, personalizing treatments, predicting disease risks, and even uncovering hidden gene-environment relationships. Without it, we'd still be drowning in genetic data with no way to connect it to real-world health outcomes. Science fiction is becoming science fact, and PLSR is one of the tools making it happen. Understanding human behavior is like trying to predict the weather, messy, complicated, and full of hidden variables interacting in ways we don't fully understand. That's where partial least squares regression, PLSR, comes in. While it's often associated with chemistry and genomics, PLSR is also making waves in the social sciences, helping researchers analyze complex relationships between variables and uncover hidden patterns in human behavior. Social science data is notorious for being highly correlated. Income is linked to education is linked to job opportunities affect mental health, and so on. Trying to isolate the effect of one variable using traditional regression is like trying to pull apart a plate of spaghetti. PLSR, however, doesn't get overwhelmed. It simplifies the chaos by reducing the data into latent variables, helping researchers focus on the most meaningful relationships without losing important information. Take survey research, for example. Suppose a study wants to understand how different social factors like income, education, and community engagement influence happiness levels. Instead of looking at each variable in isolation, PLSR extracts the key patterns that explain the most variance in happiness. This allows researchers to see the bigger picture. Maybe it's not just income that matters, but a combination of financial stability and social relationships. Another major use of PLSR in social sciences is public opinion analysis. Imagine a political campaign trying to predict voter behavior based on dozens of factors: age, media consumption, past voting history, economic outlook, social values. Traditional methods might struggle to handle this many interconnected variables, but PLSR distills them into a few meaningful dimensions, helping strategists understand the real drivers behind voter preferences. And let's talk about economic studies. Economists deal with vast amounts of data, consumer spending, inflation rates, employment figures, all of which are linked in complex ways. PLSR helps by identifying the main economic forces at play, reducing dimensionality while preserving predictive power. Instead of drowning in raw data, economists can extract the most important trends and make better predictions about future economic conditions. PLSR is also valuable in psychology and behavioral research, where experiments often involve large data sets with overlapping variables. For instance, studying the impact of social media on mental health isn't as simple as looking at screen time. It involves psychological factors like self-esteem, social comparison, and online interactions. PLSR helps researchers untangle these effects and identify which factors are truly significant. So, why does this all matter? Because society is complex, and traditional regression models often oversimplify human behavior. PLSR, on the other hand, embraces the messiness, allowing researchers to uncover deeper insights that might be missed with standard methods. Whether it's understanding public opinion, predicting economic trends, or analyzing the psychology of human decisions, PLSR is proving that numbers can, in fact, help explain people. Building a model is one thing, but trusting it? That's a whole different story. You wouldn't buy a car without test driving it first, and you definitely shouldn't trust a partial least squares regression (PLSR) model without making sure it actually works. That's where model validation comes in, the process of checking whether your PLSR model is reliable, accurate, and not just making things up. Let's dive into the key techniques used to validate a PLSR model and why they matter. First up, cross-validation, the MVP of model validation. The idea is simple. Instead of using all your data to train the model, you split it into chunks, train on some parts, and test on the others. By rotating through different training and testing sets, you get a much better sense of how well your model generalizes to new data. If your model performs well across different splits, you can be more confident that it's not just memorizing the training data, it's like practicing for an exam with different test versions. If you score well on all of them, you actually know the material. Next, we have permutation tests, a technique to check whether your model's predictions are actually meaningful or just statistical noise. Here's how it works. Shuffle your response variable so it's randomly assigned to different predictors, run PLSR again, and compare the results to your real model. If the shuffled model performs just as well, then congratulations. Your model isn't special, and you might as well be making predictions with a dartboard. But if your real model significantly outperforms the shuffled ones, that's solid evidence that it's capturing meaningful relationships. Then there's model assessment using performance metrics, things like R-squared, root mean square error, RMSE, and prediction accuracy. R-squared tells you how much of the variance in your data is explained by the model, while RMSE measures how far off your predictions are on average. A good model should have a high R-squared and a low RMSE, meaning it captures real patterns without making huge mistakes. If your model's RMSE is sky high and R-squared is embarrassingly low, well, it might be time to rethink things. Another important check is overfitting detection, because let's be honest, sometimes models get too good at fitting the training data. If your model has near perfect accuracy on training data, but flops when given new data, that's a red flag. Cross-validation helps catch this, but another trick is to compare performance on training versus test data. If the gap between them is too wide, your model might be overfitting, kind of like a student who memorized all the answers from last year's exam but fails miserably on a new test. At the end of the day, a model is only as good as its validation process. You don't want a PLSR model that looks good on paper but collapses when faced with real-world data. That's why cross-validation, permutation tests, performance metrics, and overfitting checks are essential steps before trusting any predictions. Skip them, and you might as well be making educated guesses. Do them right, and you've got a model that actually means something. So you've built your partial least squares regression, PLSR, model, validated it, and now you're staring at the output wondering, what does it all mean? Welcome to the world of result interpretation, where numbers get turned into insights. But fair warning, PLSR isn't always the most straightforward to interpret. Unlike traditional regression, where you get a simple equation with clear coefficients, PLSR gives you latent variables, which can feel like trying to understand a song just by looking at the sound waves. Let's break it down. First, let's talk about latent variables, PLSR's secret sauce. Instead of looking at the original predictors directly, PLSR transforms them into a smaller set of meaningful components. These new variables summarize the most important patterns in your data, but they don't always have a clear-cut meaning. This means interpretation requires a bit of detective work. You have to analyze which predictors contribute most to each latent variable and how they relate to the response variable. If this sounds complicated, think of it like translating a book into a different language. You need to understand the deeper meaning, not just the words. Next up, regression coefficients. These tell you how strongly each predictor or latent variable influences the response variable. A positive coefficient means an increase in the predictor leads to an increase in the response, while a negative coefficient means the opposite. But since PLSR works with transformed variables, these coefficients don't represent direct relationships like in multiple linear regression. Instead, they reflect the importance of the underlying patterns captured by the latent variables. Then we have model fit metrics, things like R-squared and root mean square error, RMSE. R-squared tells you how much of the variation in your response variable is explained by the model, higher is better, while RMSE measures how far off your predictions are on average, lower is better. A good model should have a high R-squared and a low RMSE, but be careful. PLSR can sometimes overfit if you use too many components. Always compare your training and test results to make sure your model isn't just memorizing patterns. Another key piece? Significance levels and variable importance. If you want to know which predictors actually matter, look at variable loadings and VIP scores, variable importance in projection. Loadings tell you how much each predictor contributes to a latent variable, while VIP scores rank predictors based on their overall importance. If a variable has a high VIP score, it's probably playing a major role in the model. If it's low, it might just be along for the ride. Finally, let's talk about visualization, because let's be real, numbers alone can be a headache. Graphs like biplots, scatter plots of predicted versus actual values, and loading plots can help make sense of your model's output. These visuals can show you which variables group together, how well your model predicts new data, and which predictors have the most influence. If interpreting raw coefficients feels like decoding ancient scrolls, let the graphs do the talking. At the end of the day, interpreting PLSR results is part science, part art. It takes a bit of effort, but once you get the hang of it, you'll start seeing the bigger picture, how different predictors interact, which ones truly matter, and how well your model is performing. Skip this step, and you're just blindly trusting numbers. Do it right, and you'll unlock valuable insights hidden in your data. A great model is useless if you can't actually run it. Luckily, Partial Least Squares Regression, PLSR, isn't some exclusive club for hardcore statisticians. There are plenty of software tools that make it accessible, whether you prefer coding, point-and-click interfaces, or something in between. Let's go over the best tools for implementing PLSR and why you might choose one over another. First up are the go-to language for statistical computing. If you're serious about PLSR, R has some of the most powerful and flexible implementations, especially through the PLS and Carré packages. These allow you to build, validate, and interpret PLSR models with just a few lines of code. The downside? You need to be comfortable with scripting. If the thought of writing PLSXY and comppercorp3 makes you nervous, R might not be your first choice. Then there's Python, which has become the dominant language in machine learning and data science. The scikit-learn library provides solid support for PLSR through its PLSR regression function, and it integrates beautifully with pandas, NumPy, and other data manipulation tools. Python is perfect if you want to combine PLSR with machine learning pipelines or automate analyses, but if you're looking for deep statistical diagnostics, R might still have the edge. For those who aren't into coding, MATLAB offers a user-friendly environment for running PLSR. With built-in functions and graphical interfaces, MATLAB makes it easy to build and visualize PLSR models, which is great for engineers and scientists who want powerful analytics without diving deep into programming. The catch? MATLAB isn't free, and its syntax can feel a bit weird if you're used to Python or R. If you want full-on statistical software without writing a single line of code, SPSS and SAS both support PLSR, offering point-and-click interfaces that guide you through the process. These tools are widely used in business and academia, especially by people who need results but don't want to mess with coding. The trade-off? They're expensive and their flexibility is somewhat limited compared to R or Python. And let's not forget Excel, which, believe it or not, has some PLSR functionality through add-ins like ExcelStat. While Excel isn't the best choice for large-scale PLSR modeling, it can be a useful tool for quick, small-scale analyses, especially for those already comfortable with spreadsheets. So, which one should you use? If you want power and flexibility, R is the best choice. If you're integrating PLSR into a broader data science workflow, Python is the way to go. If you prefer an interactive, engineering-friendly environment, MATLAB has you covered. Need a business-friendly, non-coding approach? SPSS or SAS will do the job. And if you're a spreadsheet warrior, well, Excel's got an add-in for that. At the end of the day, the best tool is the one that fits your workflow. PLSR is powerful no matter where you run it. You just need to pick the right tool for the job. The world of data never stands still, and neither does Partial Least Squares Regression, PLSR. As datasets get bigger, algorithms get smarter, and industries demand faster, more interpretable insights, PLSR is evolving to keep up. Let's take a look at where PLSR research is headed and how it's shaping the future of data analysis. One of the biggest trends: machine learning integration. Traditional PLSR is great at handling high-dimensional data, but what happens when you combine it with deep learning? Researchers are now experimenting with hybrid models that merge PLSR with neural networks, boosting its predictive power while keeping the interpretability advantage. Imagine a model that can handle massive genomic datasets like a deep learning system, but still gives you meaningful relationships between variables instead of a black box answer. Another major direction is big data scalability. Classic PLSR wasn't exactly designed with billion-row datasets in mind, but with advancements in parallel computing and cloud-based analytics, it's becoming more feasible to apply PLSR at scale. Expect to see more high-performance implementations that can handle real-time data streams, making it even more useful in fields like finance, environmental monitoring, and large-scale industrial applications. Speaking of real-time data, automated variable selection is another hot topic. Right now, choosing the number of components in a PLSR model is part science, part art. Researchers are working on adaptive PLSR techniques that can automatically optimize model complexity without overfitting, reducing the trial and error involved in model tuning. Think of it as a self-driving car for regression. No more guessing how many components you need. Then there's the push for better model validation. Cross-validation works well, but new techniques like stability selection and bootstrapped PLSR are improving reliability, especially for small sample sizes. These methods make sure that your model isn't just finding patterns by chance, leading to more trustworthy predictions. PLSR is also making waves in new application areas. Traditionally used in chemometrics and genomics, it's now being applied to social media analytics, economic forecasting, and even AI-driven customer behavior modeling. As datasets grow more complex and interconnected, the ability of PLSR to extract meaningful relationships from correlated variables is becoming more valuable than ever. And let's not forget interpretability improvements. One of the biggest criticisms of PLSR is that latent variables can be difficult to explain. Researchers are developing new visualization techniques and explainable AI methods to make it easier to understand how PLSR models arrive at their predictions. Think of it as upgrading from an old-school flip phone to a sleek touchscreen interface. It's the same core functionality, just much easier to work with. So, what's the future of PLSR? Faster, smarter, and more scalable. Expect to see more automation, better validation, integration with machine learning, and wider adoption across industries. As the demand for interpretable AI and predictive analytics continues to grow, PLSR is proving that it's not just an old-school statistical technique, it's evolving into a key player in modern data science. We've covered a lot, but here's the bottom line. Partial Least Squares Regression, PLSR, is one of the most powerful tools for making sense of high-dimensional, messy, and correlated data, whether you're working in chemometrics, genomics, social sciences, or even AI-driven analytics. PLSR helps uncover patterns, reduce complexity, and improve predictions. But like any great tool, it has its strengths and weaknesses. Let's start with the advantages. PLSR is a lifesaver when dealing with multicollinearity, meaning it doesn't panic when predictors are highly correlated. It also works well with small data sets, handles dimensionality reduction, and can still produce meaningful predictions when other methods fail. Plus, its ability to maximize covariance between predictors and response variables makes it incredibly effective for complex real-world applications, but it's not all sunshine and perfect regression lines. PLSR has its limitations. Interpretation isn't always straightforward, since latent variables don't always map neatly back to the original predictors. There's also a risk of overfitting, especially if you include too many components. And while PLSR is great for making predictions, it may not always be the best choice when you need a model with clear, directly interpretable coefficients. So, where does PLSR shine? In high-dimensional data sets where traditional regression methods struggle. It's widely used in chemometrics to analyze chemical compositions, in genomics to identify biomarkers, in social sciences to model human behavior, and even in economic forecasting. Basically, if your dataset looks like a tangled mess of relationships, PLSR is your best bet for making sense of it. Looking ahead, PLSR is evolving. Machine learning integration, better interpretability tools, and scalable big data solutions are making it even more powerful. As industries continue to demand faster, smarter, and more interpretable models, PLSR is proving that it's not just a statistical relic, it's an essential tool for modern data science. And that's a wrap. If you've made it this far, you now have a solid grasp of what PLSR is, how it works, and when to use it. So the next time you're drowning in a sea of correlated variables, just remember, PLSR is here to help.